Okay, I'm Geoff Blewitt. I'm a professor at University of Nevada, Reno. Well, I just finished my PhD in high energy physics at Caltech, and I had to find a job pretty quickly. Otherwise, I was going to be shipped back to England. And it turned out I went to a work fair at Caltech and interviewed with JPL. And they were looking for somebody who could do point positioning with very high precision, but they didn't have any software to do that, and so they needed somebody to develop it. And it turned out I'd done something similar in high energy physics. I was point positioning these high energy physics events in detectors and using nanosecond timing, which isn't really that dissimilar from GPS. So that's really what got me into it, was sort of the technique side of things. Well, I certainly do call myself a geodesist. I mean, when I was doing my PhD, I called myself a physicist, but I call myself a geodesist because I strongly affiliate with the geodesy community, and it's a fantastic community. It's international. The only way geodesy works is if everybody's sharing data around the world. You can't do anything on your own, so it just means naturally it's a great community. So to call myself anything but a geodesist wouldn't make any sense at all. I get asked when I first started using geodetic techniques for my research, and I don't look at it that way. I was really the one who was developing the techniques, and I must have spent the first 5 years of my job just literally developing the techniques and not thinking about the applications too much, because it was a big problem. And when I first started on this, we couldn't really do anything but position a receiver to within a few tens of meters. And by the end of maybe 5 years, we could position down to a centimeter. So it was a big difference, and once it was at that level, I could start thinking about how to use it. But I was one of many people who wrote this massive piece of software for NASA, and that is the tool I use today, and it's still being developed. It's millions of lines of software code, and now we're positioning at the 1 millimeter level every day. And we can track how things move at a fraction of a millimeter every year. So all that work I did at the beginning of my job turned out to be useful to me even now. So. Well, it's interesting you asked me that, because I've almost come full circle from physics through geodesy and back again, because my most recent project is to search for dark matter, cosmological dark matter, as it passes through the solar system. When it does that, there's a possibility, and some theories, that it would actually affect the phases of atomic clocks. So as this dark matter passes through the whole GPS constellation, which is about 50,000 kilometers wide, it would cause a sweeping change in all of the clocks over a period of a few minutes. And so that's something that I'm looking for right now. It's a really exotic application and not typical at all. But that's kind of atypical has become typical. When GPS was first devised, it was for the military. Then it became a civilian application, and high precision geophysical application. And so we used to think of GPS as being for measuring plate tectonics, earthquakes, that kind of thing. And of course, I still do that. But not only me, but lots of other people have found a million different ways to use GPS, and the applications are getting quite exotic. One of the most important problems that we're attacking right now is the problem of sea level rise. And in order to do that correctly, you have to know not only what sea level is doing, but what the land is doing. So the coast is moving up and down quite often just as much as the sea is moving up and down. And you also have to know where the center of the Earth is to within a fraction of a millimeter and be able to track that in time. I could go through a list of a whole bunch of applications, and I've got many projects going on at any given time. And I can't predict what I'll be doing next year because it's just always changing. Well, there's been quite a revolution in plate tectonics because of GPS. Before there was space geodesy, you had to rely on geologic data and be looking at average movements over the last few million years. And it appeared from that data that the plates were rigid. There was maybe a dozen plates around the world. Once we got GPS and could actually measure things, at first it looked, yeah, like that's a pretty good theory, rigid plates moving around the world. But now you can count over 50 plates around the world. It's not just a dozen. And even those plates are deforming significantly inside of them. As these plates collide and you get the Himalaya thrust up in Asia, and because they're thrust up so high, they're putting enormous load on the Earth's surface, and the Earth is deforming and flowing like a river. So I think it's given us a new insights into how the Earth is actually working. That's probably, to me, one of the most amazing things that GPS has done for us. I think along similar lines, we used to think that strain built up, the Earth would then crack, and then an earthquake would occur, and then it would lock again, and that would be that until the next one. And it was about maybe 10 years ago, maybe around 2001, 2002, that silent earthquakes were discovered. And that was because of GPS. Because by definition, if an earthquake's silent, you don't hear it with the seismometers. So the Earth's not vibrating. But the earthquake is slowly taking place, and it may be over a period of a few weeks. So that's revolutionized the way that we understand where two plates come together, what can happen. Sometimes there are these abrupt large earthquakes, and sometimes they slowly grind past each other. You asked me about three. I'm going to fumble here because I've got to collect my mind. Well, I think geodesists at the beginning were kind of running off doing their own thing. And so there wasn't really any standards to how they were doing things, and it wasn't clear how you could compare your results with somebody else's, and it wasn't clear whether the best practices are being followed. I think one of the best things that UNAVCO has done is provided those standards by testing all the commercial equipment out there and making sure that we're using the best equipment that we can use. Making sure that the equipment's being used in the best possible way, and making sure that the stations, the GPS stations that are attached to the solid Earth are attached in the best possible way, so that what you're looking at is not just some kind of local movement, it's really what's happening with the Earth. And UNAVCO has really set the standard on all of those things, on the equipment and on developing these stations. And also I should say, without UNAVCO, it would have been very difficult to get access to all the data that you need to get to put together to do your scientific investigation. And because of the UNAVCO community, everybody's freely exchanging data, and UNAVCO's done a great job of archiving that data and making sure that you can find the data that you need. I think also a third thing that the UNAVCO has done is provided a forum that brings together scientists regularly at workshops, and we exchange ideas on best practices. We exchange our excitement about the scientific projects we're doing, and we all learn from each other. And the whole community benefits from that. Wow, geodesy has changed so much over the last 30 years, it's unbelievable. We might have started off with a handful of maybe 3 receivers that were being shared by everybody. And now we have, we have more than this, but I am personally processing data from over 12,000 stations every day around the world. And the growth is exponential. That number doubles roughly every 3 or 4 years. So we as a community have lived through that and with that, and we embrace it. And just like a lot of other communities, like computer science, for example, how the it's called Moore's law, where the rate of expansion is growing, is doubling every few years, and what you can do with computers is doubled. Fortunately, that has saved us, because we can use that kind of expansion in information technology to help us to solve our problems. So we've managed to keep up no problem with this sort of data explosion. But we've also had to change the way we do things. When we only had 2 or 3 or 4 stations that we had to process, and maybe we would gather data for a week every year or something like that, we would have the luxury of looking at every single data point by eye. Or we could get a bunch of graduate students to try to look at everything and fix up all of the problems, and interactively make sure that we got a clean data set so that we could get the best possible results. And of course, that's no longer possible. Everything has to be automatic. We very rarely look at the raw data anymore, and unless if we're doing something special, or if there is a problem that we're trying to debug. And so that is totally different too, is the whole automation of data processing. And we've had to be very clever about computational techniques. When you double the number of GPS stations that you're processing, it used to be that the computational time would go to the power of 3. So in other words, if you double the number of stations, the computation goes as a factor of 8, and so on. And it becomes almost impossible to process data beyond a few dozen stations using the old methods. So we had to devise techniques where if you double the number of stations, it only doubles the number of computations. And that process really took hold, made major advances in 1997 when precise point positioning was invented. And then through a series of technological developments, it was refined until as late as 2010, where we could actually connect phases between receivers and get the best possible results that would be exactly the same results that you would get if you'd done it the old way, where it was to the power 3. So we've managed to handle that data explosion. Some might have called it a data crisis. I wouldn't call it that. A crisis to me would be you have no data. But I have no problem with data explosions, and I think that's been one of the challenges for us, and that's been perhaps the biggest change. And in tandem with that, because we have so much data, there's so many things you can do with it. And the community's been extremely creative in inventing new ways to use the data for different parts of science. And so the definition of geodesy is not what it used to be. The classical textbook definition is to do with the shape of the Earth and its gravity field and the rotation of the Earth in space, and how all of that changes in time. And yes, that's still sort of at the core of geodesy, but also geodesy is very heavily based on space-based measurement techniques. And you don't have to just apply it to the shape of the Earth. You can look at the atmosphere. You can synchronize atomic clocks across the world to within a fraction of a billionth of a second. And you can actually, as I was saying earlier, you can look for exotic things in physics too, like dark matter. It's hard to predict what geodesy is going to look like in the future. So certainly some of the things we're doing today we will always be doing because of the societal relevance of the problems that we're addressing, such as how fast is sea level rising? Is it accelerating? We're not quite sure about that yet, although it's certainly starting to look that way. And those kind of things, like earthquakes, we're always going to need to monitor them. And we're getting to the point where we can start to provide early warning, so we're getting faster at things. We're going more to real time. And 30 years ago, we'd be quite happy if it took a year to process our data. And a few years moving on from 30 years ago, okay, we'd want the data in maybe a month. And then it became unacceptable to wait that long, and we're getting to be happy with a couple of weeks. But now we're starting to get impatient, and we want our results within 10 seconds. So that seems to be where things are going. It's much faster results and much higher rates. We no longer just want to know how a station moved from one day to the next. We want to know how it's moved from 1 second to the next, or maybe even 1/10 of a second to the next. So things are getting faster and faster, and this leads to more and more applications.